All right, so let's talk about measurement because measurement's very important. It's very important when you're selecting statistics and interpreting statistics that you know the measurement scale of your variables because it determines what statistics are valid, what statistics you can use, and so on. So you need to know about measurement. And so what is measurement? Well, first of all, we need to talk about mathematics because measurement is assigning numbers to things, as we'll give a definition in a second. And the reason that we're doing that is so that we can translate something about nature into mathematics and then use mathematics to understand that element of nature. So mathematics is the study of formal systems. And a formal system is just a system of abstract entities. Numbers are an example of such abstract entities and their relationships as defined by axioms or proven through the use of axioms to begin with. You only have the axioms to begin with, and you use those axioms to make proofs. But then once you have some proofs accumulated, you can use those proofs and your axioms to further prove stuff. So sometimes we get lucky. And this is something that's most people don't think about, I think. I didn't think about it until I read Alfred North Whitehead. But it's sheer luck that mathematics actually works for anything in the natural world. So sometimes we get lucky, and parts of a formal system correspond to parts of the real world. In other words, we say that they model that part of the real world, and we can use that model to then understand that part of the real world. An example is counting stuff. How many goats do I have? How many sheep do I have? How many cows do I have? Another example is Newton's law of gravity. You see there. You don't need to know anything about that equation. You just give it as an example. Here's a part of a formal system that actually corresponds to the real world. It gives the force that two physical bodies exert on each other through gravity. Since math sometimes applies to nature, we can use our understanding of math to understand nature. And just an absurdly simple example, the relationship between 5 cows and 10 cows is similar to the relationship between 5 chickens and 10 chickens. So we don't need to learn separately about cows and chickens in order to understand that 10 is twice as many as 5. Whether it's chickens, cows, or even if we discovered a brand new species, without knowing anything else about the species, we could still count it. So we don't need to learn independently about cows and chickens to count both. In order to do this, though, in order to leverage our understanding of math to understand nature, we have to translate nature into math. And the way we do that is measurement. Measurement means assigning numbers to aspects of nature according to a set of rules. And I've already talked about counting. That is an example. Given a set of things, place the integers in a one-to-one correspondence with each member of the set until all members of the set have been paired with an integer. The final integer is the number of things in the set. We use this rule so often that we probably don't even think about counting as an act of measurement, but that is in fact what it is. It's taking the measure of the number of things in the set. All right, so what is it that we can measure in nature? Well, two things. We can measure variables and we can measure constants. So a variable just means anything in nature that isn't always the same. It's not uniform, it's not homogeneous, it can have different values. And some examples of variables, gender, intelligence, personality, time, place, elevation, emotional state, these are all things that are variable. A constant is anything that does not vary. Now, sometimes, in other words, it always has the same value. Sometimes this is only in the context of a particular study that something is a constant. We can treat personality as a constant in psychology, for example, even though over a lifetime a person might go through some personality changes. But within a 1-hour study in psychology, your personality is going to be pretty stable throughout the whole thing. But some things are only one value and it's universal. Anywhere you go in the universe, it would be the same. At least as far as physicists know now, or more technically, at least as far as I know that physicists know right now. An example of that would be Planck's constant. Some physicists may correct me in the comments or something. Maybe Planck's constant's not constant, but I think it is everywhere in the universe, as far as we know. Okay, variables can be continuous or discrete, Continuous means able to take on any real value. And so you're going to have to think back in your head to the real numbers. What does that mean? Well, it means basically any number. 1 is a real number. 1 is also an integer, but real numbers can be non-integer values. For example, 1.01, 1.001, 3.72415, and so on. So those are the real numbers. Some examples of continuous scales: thermal energy, the time it takes for rats to learn a maze, height. All of these things can be measured continuously, up to some limited precision. Okay, discrete, meaning able to take on only integer values. So remember back to the integers. That means only 0, 1, 2, 3, and so on. No fractions, no decimals, just the integers. Examples of discrete variables: physical state, solid, liquid, gas, plasma. Number of people in a group. You can have 20 people in a group. You can have 21 people in a group. You cannot have 20.1 people in a group. Number of rats who learn a maze, etc. Now you may be saying to yourself, physical state, wait a minute, those aren't numbers. Those are words. Right. But that brings me to the types of scale, because we could replace those with numbers, right? I could call solid 0, liquid 1, gas 2, plasma 3. So that brings me to scales and the types of scales. So a scale is a standard of measurement, or a standard for measurement, with certain qualities. And we typically talk about 4 types of scale: the nominal, ordinal, interval, and ratio. And they're in that order, not accidentally, but actually as we descend that list, each scale brings with it all the properties of the prior scales plus one new additional property. So for example, the nominal scale can only distinguish classes of things. That's all it can do. If we go back to physical state, solid, liquid, gas, plasma, that would be an example of a nominal scale. So I could replace it with numbers, or I could use the words. It doesn't matter. The numbers are meaningless. Nevertheless, it still fits my definition of measurement, because I could use numbers even though the numbers don't actually mean numerosity of any kind. The ordinal scale can rank order data from least to most, or from most to least, of whatever the thing is we're measuring. It can also distinguish classes of things. So an ordinal scale can do both. It can rank order and it can distinguish classes of things. The interval scale means that intervals between adjacent ranks are equal. So addition and subtraction now are sensible on an interval scale. Interval scale can also rank order data and can also distinguish classes of things. And finally, we come to the ratio scale. The ratio scale has a true 0. And what I mean by true 0 is 0 means the absence of the thing being measured. 0 means none of it, whatever it is that you're measuring. When you have a true 0, that's when you can talk about ratios. So, for example, twice as much, half as much, and so on. Only if 0 means the complete absence of the stuff. And ratio scales also have equal intervals between adjacent units. Ordinal, they can rank order the data, and they can distinguish classes of things. Okay, some examples. Examples of nominal scales: gender, ethnic group, academic class, any group membership. Your name is an example of a nominal scale. I could replace your name in a data set with the number 3. And as long as I don't use that number 3 for anybody else in the data set, perfectly valid nominal scale. Ordinal scales. Race finishes. Did the person finish first, second, third, and so on. Science fair places, those sorts of things. Interval scales. Temperature in Celsius or Fahrenheit. Another very well-known scale that we at least treat as interval, although there was some controversy in statistics back in the 1950s, 1960s over whether these were truly interval scales or if they were only ordinal scales, but the so-called Likert scale. Now, if you're not familiar with Likert scales, have you ever answered a question? I want you to answer this from on a scale from 1 to 7, 1 meaning strongly disagree, 7 meaning strongly agree. Likert scales are dumb. 1 to 7. Well, that was a Likert scale. So, and we treat those Likert scales as if they were interval scales. They do not have a true 0, so we can't say that somebody who circles a 6 on that scale agrees twice as much as somebody who circles a 3 on that scale. That statement doesn't make any sense, because there is no 0 on that scale at all, much less a true 0. And as far as temperature, Celsius and Fahrenheit, 0 on those scales does not mean the complete absence of thermal energy. In the Celsius scale, it means the triple point of water, the point at which water can be in three states at once. It can be in solid, liquid, or gas. And in the Fahrenheit scale, I don't know if there is a meaning. There probably is, but I don't know what the meaning of 0 is in Fahrenheit. Since water freezes at 32 degrees Fahrenheit, 0 is really, really cold in Fahrenheit. Anyway, examples of ratio scales. Temperature in Kelvin. So in Kelvin, 0 Kelvin really does mean the complete absence of the molecular energy that we call thermal energy. There is none of it at 0 Kelvin. Electrical potential of the electroencephalogram, time to finish a race. So going back up here to race finishes, the person who came in fourth was not twice as much as the person who came in second and half as much as the person who came in eighth. That doesn't make any sense. But the person who finished the race in 5 minutes was twice as fast as the person who finished it in 10 and half as fast as the person who finished it in 2.5 minutes. So time to finish a race is a ratio scale. 0 on a time scale, any time scale, really does mean no time has elapsed. Frequency, meaning the number in class, not meaning cycles per second. Although this next frequency does mean cycles. I believe that's what cycles over distance. Frequency of electromagnetic spectrum, and so on. Those are all ratio scales. So, once we've assigned a number according to a rule, what have we got? Well, you've got a datum. So a datum is a single number assigned to something in nature according to rule. In other words, a record of a single measurement. Now, a little bit of a note about the way people talk about this stuff, because it's important to understand what people are saying. Measurement, that word measurement, is often used to refer to the act of assigning a number according to a rule. In other words, like I took a measurement or I measured that thing. But it also sometimes refers to a datum, or sometimes a measurement can even refer to a statistic. So another word for datum or statistic is observation. And, of course, a datum is a record of a single measurement. Once we have more than one datum, we have data or data. You can say data or data, either one's correct. Data or data, I say data, is a collection of measurements. In other words, the plural of datum. So, you want to note this, data are, not is. In other words, the data are consistent with my hypothesis, not the data is consistent with my hypothesis, and so on. Data were, not data was. Okay, and that is measurement.